Hello, and welcome to my presentation on agent-based control of diverse demand in additive manufacture systems. My name is Chris Snyder, and I am presenting this work on behalf of the lead author, Martins Obi. This work is concerned with the concept of big demand, the increase in demand for a product or products greatly in excess of that which can be produced through current production, therefore requiring new production means to meet demand. Where a demand scenario occurs, current production and logistic systems are insufficiently flexible or too small to produce components at the rate required, both meaning that the demanded product is not delivered and that production of other products is slowed while the system struggles to cope with the highly demanded lines. As part of the Brokering Additive Manufacturing project at the University of Bristol in the UK, we are investigating if and how such big demand may be dealt with through agent-based control of nationwide additive manufacturing networks. Big demand scenarios are most obvious from the last few years when we've seen major disruptions to global supply chains that have led to hugely increased demand or demand far outpacing production capability. Early in the pandemic, the UK struggled to produce PPE at the rates in which it was used in hospitals, leading to a national shortage. This demand was eventually met through the concerted efforts of hundreds of fab labs and small producers using additive manufacturing, who then passed products onto the hospitals in their local area. Big demand is, however, a broader concept that is visible across global production lines. Shifts in supply lines and production capability regularly occur at meso and macro levels and limit ability to meet a change in demand, such as can be seen in chip manufacture and the automotive sector currently. Further, future trends such as mass customization also create potential for demand of certain product variants to outstrip the capacity to produce them. This project seeks to explore one way in which big demand may be met, through agent-based distributed manufacturing networks that leverage many thousands of underutilized machines around the UK and beyond. In so doing, it seeks to meet three aims: to explore how such systems may meet big demand, to create production systems and logics that can accommodate highly dynamic constraints and changes in system capability, and to facilitate independence of all producers such that all may concurrently work together to meet big demand rapidly. This project is based in the additive manufacture space. This technology has proven benefits for big demand: high flexibility of production capability, low barrier to entry and setup cost, and a diverse and extensive national network of machines that may be deployed rapidly. Even without any form of national control, the UK additive manufacture capability has already proven its power through supporting the needs of the PPE crisis during the pandemic, something that traditional manufacturing capability failed to achieve on its own. AM capability comprises many thousands of machines of different technologies and capabilities. These are housed in a range of sites at a range of scales, from hobbyist level fabricators who use production machines at home, to educational institutions using machines for teaching and in-house production, to a range of industries across design and supply using high-end machines to create parts for real products. These machines create a large, flexible, and highly variant capability, but are currently essentially standalone systems that work as individuals. This project looks at how we can link these systems in a national network of AM capability to maximize capacity. The paper we are presenting here focuses on modeling of the agent-based system that we are trying to create in order to maximize its value. As part of a larger body of studies, we are modeling the UK AM capability as an agent-based system to understand the impact of different operational logics, parameters, information sets, rule sets, and constraints on eventual production capability and reaction speed. This work sits aside several studies on the performance of the system, including one other at this conference presented by Dr. James Gopsall, looking at the effect of performance when also accounting for operational hours and uptime of the machines. In previous works, we have demonstrated that agent-based methods are fundamentally capable of meeting big demand scenarios for an extended additive manufacture network. If you would like to know more about our past works, please contact us directly. This work itself seeks to increase realism of our existing models and explore the impact of further variable sets and constraints on the system. Previous works have typically considered the AM systems in the agent-based system to be homogeneous, with all machines having identical capabilities and all jobs having identical requirements, and therefore all machines able to fabricate all jobs. Here by jobs we mean any request for a component to be additively manufactured, and a machine is typically considered a single additive manufacturing capability or machine. This homogeneous structure, of course, does not really reflect reality. AM capability is highly diverse, with many different types of machines, each with different accuracies, material compatibilities, reliabilities, and associated costs. Equally, the requirements for each job can be highly variant, specifying different tolerances, materials, technologies, quality requirements, or levels of certification, amongst many other parameters. This creates substantial compatibility constraints that may limit emergent system performance. Circumstances, each job will be assigned to a machine with matching compatibility, much as occurs in traditional production. This requires knowledge both of the types of machine available and of the requirements of incoming jobs to ensure that all demand may be met. With a consistent demand, it would be fairly straightforward to plan the required scale of capability across all types of machine setup according to the typical incoming job profile. Where there are more jobs of a specific set of configurations, more machines of compatible configuration would need to be installed to meet the demand. This changes, however, in a big demand scenario. When the demand for a specific job type increases substantially, those machines of compatible type may no longer be able to meet the demand with their current resource. The system requires an increase in machines of a certain compatibility set. Here, the flexibility of AM systems creates an opportunity for the system to adapt to the change in demand. While they're set up for a single configuration, many AM systems are capable of broad compatibility with different types of job. Typically, jobs will vary in the material that they require across some range of polymers, and it is a simple process to change filament on the machine or recalibrate to reconfigure its parameters. Similarly, while the accuracy of many AM systems is not high relative to traditional manufacture, it can be improved to sub-millimeter accuracy for many printers even at the consumer end of the market by careful recalibration prior to starting the job. In order to meet big demand, this creates the option to switch from a system where jobs are assigned to a compatible machine to one where the machines can request a change in their compatibility to meet the incoming job profiles. This change is not, however, free. Any change in materials or configuration will reduce uptime and incur a cost that must be accounted for to ensure overall system performance. This scenario leads to the research questions of this work. Can allowing machines to transition compatibility allow this project to support big demand across job machine and variants? And when should machines request a transition to maximize emergent performance of the whole system? To investigate these questions, we created an agent-based system using AnyLogic. The system was configured as a machine-led coordinated system where machine agents communicate directly with job agents. In this configuration, machines may accept a job of corresponding compatibility to themselves or may request a change to a different compatibility. This change incurs a dwell time while the machine waits for it to be implemented. Critically, the machines decide whether to accept a job or request a change based on the total population of jobs of each type currently present in the system. When the proportion of a single job type against the total population increased above a given threshold, the machine would request to be changed to that predominant type. This ratio is here termed the transition ratio. This meant that as a big demand scenario arose, machines would be encouraged to switch types to that of the incoming demand. The model mimicked a small fabrication facility comprising 15 machines. Both jobs and machines were constrained to 3 abstracted types, where machines could fabricate all, but only when configured for each. On startup, machines were equally distributed across all 3 types. Jobs of each type were created with a 5% probability during each time step, creating a steady-state demand profile. Machines select jobs from the population using a simple first-in, first-out selection logic. And at time t equals 2000, the likelihood of creation of job type C was increased to 30% to mimic a big demand scenario. For each set of experimental runs, machines were set at a different transition ratio, from 20% of the total population, indicating a machine that is keen to change, to 80% of the total population, indicating one that is resistant to change. All machines were set at the same ratios for each experiment. Looking next at results. For experimental runs with a high resistance to change, we found that the system was not able to cope with the big demand scenario. On onset of big demand, a large proportion of machines would switch to the highly demanded type. This meant that the big demand was quickly met, but the other types of job then found themselves without machines to accept them. After the big demand scenario, the proportion of types A and B, those not in the big demand, were approximately equal. Neither ever produced a large enough proportion to incur change requests to their own type, and so the system became swamped. This was not the case when the machines were keen to change. At a ratio of 20%, the onset of big demand caused near all machines to switch to the demanded job type. This led to the big demand quickly being met. As with the previous case, the switch to the demanded type caused a large increase in time and system for the non-demanded job types. But once the demand subsided, the machines readily requested a change back to these types and caused the whole system to return to a steady state. This was similar for a ratio of 40%, but with one important difference. In the previous case, the readiness of machines to switch types led to an accumulation of incurred costs as machines waited for their reconfiguration. In this case, where machines were slightly more resistant to change, the overall system returns to a steady state faster as fewer machines request to change. In this case, the system returned to a steady state in approximately 65% of the time of the previous case. We can also observe a concerted effort from the machines just after the big demand scenario to process the backlog of undemanded types, where their proportion has built up significantly above the threshold while the system focused on the big demand. To understand these results, it is important to consider the expected proportionality of each job type. As there were 3 types of job, each set to equal likelihood of creation during steady state, we would expect the total proportionality of each against the whole to be around 33%. Against this value, we find that a threshold ratio that is lower creates a system that will process all jobs and meet a big demand, but will accumulate change over cost. That a ratio far above will create an unstable system that cannot process all jobs, and that a ratio slightly above will process all jobs while also remaining suitably unwilling to change to minimize additional incurred cost. This has implications for any agent-based AM system in that in order to maintain stability or optimize behavior, there must be some knowledge of the expected incoming profile of jobs to allow machines to manage their willingness to change appropriately. For our agent-based system, and in relation to our research questions, this leads to 2 conclusions. First, agent-based control of AM capability is suitable to meet big demand scenarios even when accounting for variant machine and job compatibilities. Second, to meet big demand scenarios, the expected profile of jobs outside of the big demand scenario must be known to control the willingness to change and ensure optimal overall system performance. It suggests several areas for future research and development. The results suggest that low-demand job types are at a disadvantage in the agent-based system, as currently configured, as their proportionality is unlikely to ever increase such that machines request a change to their type. Further incentivization or cost modeling may be required in broader or larger systems to ensure that all jobs are processed. It's also clear that the willingness to change of each machine can have a significant effect on overall system performance. When big demand is present, it is critical that machines within the system demonstrate emergent collaboration to produce products as quickly as possible. Should machines be entirely free to choose their own willingness to change or have imperfect knowledge of the incoming job profile, it is possible that the willingness they choose could decrease system performance or even make it unstable. This suggests that both fully agent-based control and semi-hierarchical structures should be investigated, the latter of which exchanges knowledge of incoming job profiles and suggests transition ratios tailored to overall system performance. This work has investigated the capability of an agent-based control system to meet big demand scenarios while accounting for variance in machine and job type. The results show that the approach is capable of meeting the demand and returning the system to steady state. However, they also show that the willingness to change of machines, defined here by the proportion of jobs of a certain type in the system relative to the whole, has a significant impact on overall system performance. By modelling and understanding the incoming profile of job types and tailoring willingness to change based upon it, this work shows the potential to maximise emergent system performance in big demand scenarios. Many thanks for listening to my presentation today, and I look forward to answering your questions.